Hello, this is Long. I run the Nanofabrication facility and have been developing our fabrication service since 2011. This service is designed to make nanofabrication technology more accessible. If there is something you want to make, but don't know how or don't want to make it yourself, then this is the service for you. Before getting into the fabrication service, it is important to understand who we are. We are an academic shared laboratory. We maintain our own equipment, provide training, and support research. Our primary business is to provide an excellent research environment for our students and researchers. We conduct research to continuously improve our expertise. I have personally spent over 20,000 hours working in this lab and logged over 3,000 hours of equipment time. This does not include the thousands of hours spent maintaining, repairing, and modifying the equipment. Since I've put in the time, nanofabrication is relatively easy. Once I've created something, I can explain it within a single paragraph. This may inspire others to try. But they're in for an amazing journey that will take several years with many ups and downs. They will learn new skills and become better researchers, but the path is treacherous and many will not make it to the goal. If reaching the goal is far more important than the journey, then the fabrication service is for you. Any expert pursuing a new challenge cannot guarantee success, but they will certainly get further, faster, and using less resources. Let's recount a case to explain what happens during a fabrication service. In 2021, a client contacted me to build a MEMS microinjector for gas chromatography. I have never heard of gas chromatography before and have no clue what they are talking about, so I asked for some documents describing the device. After reviewing the publication, the device is too complex, we don't have the required processes, and we're missing a critical piece of equipment. After nearly a year of back and forth, we agreed that building the microinjector right away is too hard. This doesn't mean that it cannot be done. It simply means that it is more likely to fail because we run out of money and or time. Instead, we will build a microvalve, a critical component of the microinjector. This will allow us to focus on the minimum activities that demonstrate feasibility. Since the client has no fabrication experience, hiring my expertise will greatly de-risk the project. So what are the risks? This project has many risks, but we will only cover 3 known risks in this presentation. The first risk is expertise. I have never made a MEMS device before. I know that the author of the paper likely spent years figuring out the processes to fabricate the device. It took several weeks, but I managed to track down the dissertation in France. The process to fabricate one component of the microvalve involved 15 steps, where 8 of the steps needs to be developed. Some processes look easy to do, while I don't even have the experience to guess at the others. This is enough of a problem to slow down and think about the process of each step carefully. It turns out that the author just wanted to etch through silicon and was probably limited by the available technology or expertise. After some research, I propose using AZ12XT, a photoresist that is thick enough to etch through silicon in a single process. I am confident because I know the etch rate of silicon versus photoresist for one of our equipment. There are some concerns with AZ12XT from literature, but if it works, we will save a significant amount of cost and time while greatly increasing yield. If it doesn't work, I have some backup plans that are still far less complex than the published process. The second major risk is etching 3 different layers in silicon. The published process involves too many steps that need to be developed, and we don't have an oxidation furnace. In addition, each wafer costs $420, and the 15 weeks lead time means that we need to decide on specifications that we don't know yet, such as the valve seat height. If it is too low, the valve membrane will collapse, but if it is too high, the valve may not seal well. Another problem is that photoresist will not coat a patterned surface very well, but there is a chance that it can work for this project. Thus, I propose using the same photoresist as before. In addition, we know that the valve seat height will naturally vary across the wafer. Therefore, by evaluating the valve performance from devices across the wafer, we can determine the optimal functional range for the valve seat height. The third major risk is bonding 2 pieces of silicon together using a PEEK membrane. We don't have bonding equipment or any bonding experience, so we contacted academic nanofabrication facilities with bonders and asked for their assistance. We specified the project goals and provided an initial recipe with the paper. They considered their capabilities and recommended a different approach. Sounds familiar? Working with experts adds a new risk. Since we don't know anything about bonding, how can we evaluate the experts? A big part of the evaluation is their proof of work, as you will see in the coming slides. There are many other risks for this project, but from the risk assessment so far, it should be clear that this is an R&D project and we have crafted a pretty decent plan. However, as many generals will say, no plan survives first contact with the enemy. When executing the plan, a seasoned expert will hypothesize, observe, analyze, and adapt. The first activity is to buy photoresist. I chose a thicker formula and verified with the vendor a recipe to thin it down. It failed catastrophically since the unexposed regions dissolved. The sales guy gave me another recipe, but now the critical question is whether photoresist works at all when used normally. This is also my first time using photoresist that is thick like honey. I just scooped it onto the wafer and tried to spread it evenly. This procedure is not repeatable. I came up with many ideas and decided on a funnel. This works remarkably well and reduces the amount of photoresist used by half. More importantly, this procedure can be repeated by anyone. This last statement is the standard for processes that I create. When developing a new process, I usually begin with our own process library, the recommended process from the manufacturer's datasheet or a publication. Since I have no experience with this particular photoresist, I designed an experiment to determine the best dose. Since the UH profiler does not look assuring, I verified the results with a new profiler at Rice University. As it turns out, the UH profiler is surprisingly accurate for a 35-year-old tool being held together with tape. The critical dose is near 210 millijoules per centimeter squared, but I decided to expose at 400 for a number of reasons that are specific to this project. One big reason is to avoid unnecessary optimizations to save time and cost. I have etched silicon before, but have never tried to etch through a wafer. I started with an old process and modified it to etch through the wafer. Not all the holes were etched through as anticipated. At this point, I was concerned about damaging the equipment since etching through the wafer will expose the lower electrode to the etchant. I reached out to the academic nanofabrication community and learned about two methods to avoid this issue. Both methods require temporarily bonding the sample wafer to a carrier wafer. I didn't like either method since it requires cleaning the adhesive. The number one tip in my cleanroom is to avoid contaminating samples because it is very difficult to evaluate cleanliness. A corollary to the previous tip is that any cleaning process should be assumed to contaminate the sample unless proven otherwise. Mindfully following this tip is how I regularly achieve 100% yield. So I came up with an idea that is simpler and cleaner. The idea is to apply dicing tape to the backside of the wafer. I thought about how the idea can fail and performed some simple calculations to verify that the tape won't melt, the adhesive won't melt, and the sample wafer will not overheat. I also know from experience that the samples are never hot after etching. Although optimistic, I was thrilled when it worked on the first try. Fortunately, this process works every time thereafter, saving me time and the customer money. Nanofab users, please do not try your ideas without consulting with staff at your facility. There are many things I considered before trying my idea to significantly reduce the risk of damaging the equipment. Any mistake may cause permanent damage to the equipment that will ruin your research and anyone else who needs it. When etching through a silicon wafer, the wafer sometimes gets jammed in the equipment. The equipment needs to be opened to retrieve the wafer. A cracked wafer means days of processing is completely wasted. This problem is not repeatable, so I think about how it could happen and collect evidence whenever it does happen. About a month and many cracked wafers later, I opened the tool as soon as it happened, touched the clamp, and got burned. At that moment, I found the final piece of evidence to solve the case. Etching generates a lot of heat. The clamp gets really hot and melts the photoresist, which then glues the wafer to the clamp. This causes the wafer to tilt and jam the loading arm. Therefore, to avoid melting the photoresist, the recipe is modified to cycle between etching and cooling. Etching 3 pattern layers in a single wafer required the development of many new processes. How do we evenly apply photoresist on a patterned surface? How accurately can we align the layers? How do we align a pattern on the front side to the back side of the wafer? What is the silicon etch rate for each pattern? How do we even know when to stop the etch? All of this and more needs to be figured out to reliably produce the 3-layer wafer with 100% yield. Long story short, we figured it all out by masterfully applying the scientific method. Hypothesize, plan, observe, analyze, and adapt. Whenever I perform an experiment, I try my best to ensure that it results in learning something new that will lead to a better experiment. Every slide in the report that I provide to the customer will show what was done, what's the problem, and what was learned. When generally conducting research, we do not know if or when things will work out, but by masterfully applying the scientific method, we can certainly bring the future forward. This project took 85 hours of labor over 45 days to complete the first wafer, which contains 25 MEMS microvalve. The entire process I developed was taught to the customer who has zero nanofabrication knowledge or experience over the course of 3 days. I modified the photomask to fit 69 microvalves into a single wafer, and the customer made one wafer with nearly 100% yield in 2 weeks. The initial cost for R&D was approximately $50,000, but producing a set of 69 microvalves afterwards cost $5,500. Having the customer operate equipment and running the expertly crafted recipes saves them time and money, while freeing up my time to pursue problems most appropriate for my skills. Everything I developed for this project becomes a core technology at UHNF. These processes are what allow me to teach some of our students how to complete their projects during training. If there's something you want to make, contact me. You may be surprised how accessible nanofabrication can be. Thank you for watching.